10 kmap. Okay. So we have done normal circuits, and as I already explained you, whatever the questions you did in chapter 1, that is conversion from gray to binary, binary to gray, BCD to access 3, and if you want to convert any number into 2's complementary circuit, 1's complementary circuit, all you can design using this method. Okay. So we have done this question, and have you done this design a gray code? You did? No?
Let's stop at full adder.
Yeah, but this is before full adder. Have you done this? Hello? No? Design a binary to gray combinational circuit. And binary to gray, gray to binary, BCD to access 3, any conversion we can do using the same method. Okay. So what is the question? Design a binary to gray combinational circuit for 2 inputs. So they mention how many inputs? 2 inputs. What will you do? That you need 2 inputs, A and B. And you want to convert a binary number into gray. Okay. So output you will write gray codes in the output. Here you will write the gray codes. So now if you have 2 inputs, what will be the combinations? How many combinations? 0, 0, 0, 1, 1, 0, 1. So now the task is convert this 0, 0 into gray. How will you convert into gray? You know the conversion? Yes. So how will you convert into gray? 0, 0. Means you will get how many outputs you will get? 2 outputs. One F1 and F2. Clear or not? Okay. Then 0, 1. If you convert in gray, what will you get? 0, 1. Very good. 1, 0. 1, 1. And 1, 1. 1, 0. Yes, correct. So this is binary to gray conversion. It is here. They want for 2-bit. If they ask for 4-bit, 3-bit, you can do it. It is the same thing. Now, how many K-maps you need to solve? 2, because 2 output. If 2 output, 2 K-map, 3 output, 3 K-map, then draw the circuit. So for the first K-map, for F1, you have A and B. And then 0, 1, 0, 1. Okay. So what will be the F1 result? Okay. So what is the F1 answer?
A, B.
Really? You want AB? Hello, girls. Only A, yes. F2. 1 and 2. So what is it? This K-map is separate pair. So it is XOR or not? So you have A XOR B. So the answer will be now, you have A and B 2 inputs. Then with the buffer gate, because you have the same, so I'm using buffer gate. Means F1 is this. And what is F2? I want A, I want B with XOR. It gives me F2. Clear or not? So this is F1 and F2. So this circuit is complete circuit is converting binary number into gray. You will give input binary, but the result will be as a gray. So this is called combinations. Clear? So there are several questions in the book. Okay, in chapter 4. Try to do all the questions. The conversion. Any conversion which you learn in chapter 1, all you can design the circuit using this technique. These steps you will follow and you will get the circuit. Anyone has doubt? Yes, do you have any question? Hello? No? No question? Hmm.
How we could know what to
K-map? Look. Answer. What will you get? It's like, and do you know the table of XOR gate? No. XOR gate table, you know? If inputs are same, 0. If inputs are different, 1. Look, do we have the same or not? Can you see? So even without K-map, I can write because I know that this is the table of XOR gate. Huh? Otherwise, if you find from here, you will get the same answer. Okay. Anyone has any other doubt, any question? After that, you did half adder, you design. Half adder circuit will be like this. Everyone knows, huh? Then full adder. Full adder circuit, you design yourself? No.
just told us to
Hmm. So I didn't tell you to finish, to bring, to complete this full adder, no? Very good. So for full adder, what will you do? You have 3 input. 3 input and then how many outputs? 2 outputs, sum and carry. So 0 plus 0 plus 0. The answer will be 0, 0. Then you have 0 plus 0 plus 1. Answer will be 0, 1. 0 plus 1 plus 0. Answer will be 0, 1. Carry 0 and sum 1. When you have 0 plus 1 plus 1. 1 plus 1 means sum 0 and the carry is 1. So you will get this. Clear? Now how many K-map? 2 K-map, and then you will draw the circuit. So you will get 2 K-map. You will draw 2 K-map and you will get this. So this is the circuit which you will get. This circuit.
So no difference, only clear.
Yes, of course, everything is same. Means if I mention half adder, definitely you should use 2 in. If I mention design a full adder circuit, so I will not mention that how many inputs. You should know for full adder there are 3 inputs. For half adder there are 2 inputs. So you should know it. For full adder how many inputs and for half adder how many inputs. Clear?
Yes.
Then you will get this diagram. Okay, fine. So for full adder circuit, you have some X XOR Y XOR Z, and the carry is this XY plus XZ plus YZ. Okay. So remember this because I want to explain you other thing here. So what is the sum for the, first tell me half adder sum. So when you design the half adder sum, what was the circuit? Sum was A XOR B for the half, huh? And the carry was? Hello? You didn't do it? It is in your notebook. What was the carry for the half? XY, huh? Now, if you solve the full adder circuit, which we solved before, we find that the for full adder, sum is equal to A XOR B XOR C. And then carry is XY plus YZ plus X. Clear? Understand? So now, could you tell me if I have 2 input, the sum is A XOR B. So if I choose 3 input, then the XOR is, then the sum is A XOR B XOR C. So if I have 4 input, what will be the sum then? Very good. If I have 5 input, A XOR B XOR C XOR D XOR like this. Huh? Now, I want to implement a full adder circuit using half. I want to draw a circuit. In that circuit, I want to implement a full adder circuit using half adder circuit. So what I am going to do, I am going to represent a full adder circuit in terms of half. So I will do something with carry. Some I will keep as it is. I will do something with carry. I will show you what I will do with the carry. So I have this carry, huh? So what I am going to do, because I want to implement like half. So this carry has xy and this carry also has xy. So I will not touch xy because xy I need it. I will do something with the other terms. Got it? So for the full adder carry, I will keep as it is xy, but I will do something with yz and xz. Got it? What I'm going to do, I'm going to add here the term extra, which is missing, x plus x bar. And I will add in this term xz. What should I add here in xz? Y plus y. Now solve. So what we will get it? We will get xy plus xyz plus x bar yz plus xyz, then xy bar z. Okay. Is there anything common? xy, xy, xy. Can I take from these three terms xy common? So I will get xy 1 plus z plus z. Got it? Okay. Now I am taking these two terms, this and this. What can I take common? Z. So I will get x bar y plus xy bar. So this is XOR. So we have xy. So what is the carry? We have xy plus z x XOR y. Clear or not? I did these things and I will get this carry. So now this is the full adder carry. And full adder sum is this. A XOR B XOR C. Clear? Now look what I will do. I will draw the circuit. I will draw the full adder circuit with this new carry and the sum. So now I will draw the circuit. Here I have A XOR B XOR C. Clear? So I am going to take A and B. So I am getting A XOR B and then XOR C. Any doubt till now? Hello? Oh, it is XY, huh? Why I'm writing A XOR B XOR C?
We understand.
No problem. I will delete it. Okay. So I have X, Y, and Z. Actually, my favorite is ABC, not X, Y, Z. Okay. So X, Y, Z. And after that, I'm getting here some, which is, so here I'm getting X XOR Y. Clear, girls? So sum is, I'm getting here X XOR Y XOR Z. Now, what is the carry which we implement here? The carry is, what is the carry? XY. Clear? So I want XY. I have X. Then I have Y. And this is AND gate. This is XY. Then another carry. Z. Okay, Z is also here, already here. Then Z with X XOR Y. X XOR Y is this or not? So I will take from this X XOR Y and this Z. Then AND gate. Clear or not? And this AND gate, on this AND gate, both will be with, tell me, what should I do? Here, or. I need to use OR gate, and this is the complete carry. Clear or not? Yes. What happened? Which one? This AND gate? The second one? Yeah, it is that. Look here. Can you see? This is Z or not? Clear, girls? Now check. Can you see this circuit? This XOR and this AND. What is this circuit? Why not? Huh? Half adder. What did you use in half adder circuit? One XOR and one AND. So this is half adder or not? Okay. Now check the new. This XOR and this AND. Another half or not? Means you can say that we can construct a full adder circuit using 2. So the question can come in this way: design a full adder circuit using half adder circuit in the exam. So then you can design like this, that we can construct a full adder circuit using half adder circuit. Similarly, the question can come in MCQ form, that we can ask you how many half subtractor circuit is required to implement a full adder circuit. So you will say we need 2 half adder circuit and 1 OR gate to implement the complete full adder. Clear or not? So question can come in this way. So I did these changes in the carry of full adder just to show you this structure. Because if I didn't do any change in the carry, I will not get this structure. So I have to get this carry so that I can implement in this way. We can show you that full adder circuit can be constructed using 2 half adder circuit. Similarly, you can design now the homework you can write in your notebook. Design a half subtractor circuit is the question. Design a half subtractor circuit, comma, full subtractor circuit, and arrange the circuit in this way that you can construct a full subtractor circuit using half subtractor. And arrange a circuit in this way that you can design full subtractor circuit using half subtractor. Then again, for full subtractor circuit, you require again 2 half subtractor. It will be the same as I explained, but you have to design the full subtractor circuit with half subtractor. So first you will design half subtractor, then you will design full subtractor, then you will do something with the borrow. There will be borrow, not carry, huh? So borrow will be in subtractor. Understand the subtractor, huh? So you will design the subtractor circuit. So there will be borrow and difference. And then you can do something with the borrow, and then you will design a full subtractor circuit using half subtractor in this. Clear? Understand? Chapter 1, 2, 3. Now, design a circuit to convert BCD to access 3 code. Clear? BCD to access 3. Now, yes, any doubt? Hello? Do you have a question? No? BCD to access 3. BCD number, you know that from 0 to 9. Clear? 0 to 9, can you solve using 2 variable K-map? 0 to 9, A, B, C, D. 2 variable K-map. Then 3 variable K-map. A, B, C, D. Tell me. Here A, here B, C, D. How many combinations? 4 combinations, 0, 0, 0, 0. And you will write till 15. Okay. I want to convert this one in access 3. Access 3 meaning, do you know the access 3 meaning? 3 more. So if you want to write 0 in access 3 means?
0.
Okay. So till 9 is okay because till 9 is BCD, huh? And if you are writing 10, 10 is it in BCD? Can you convert then in access 3 10? No. So then you will use here. What will you use? Don't. That is the use of don't care. Means if the term which is not exist, you will use the don't. For BCD numbers, we can represent 0 to 9 only. Whenever 10 comes, I cannot represent in 4 digits. Clear? Even that's why I cannot get the access 3 code for this. So now after that, we will use the don't. Clear? So here you can see now. This is the truth table. So first we have A, B, C, D. I will write from 0 to 15 because 4 inputs. So 4 input, I cannot write 0 to 9. I cannot leave in the middle because I have to use now 4 variable K map. So I should write from 0 to 15 first. After that, I am converting each number into access 3. But I can convert till 9 only. I cannot convert 10 because 10, this 10 is wrong. It is not BCD. Is it BCD? Do you know it is BCD?
No.
Hello? Yes. Huh?
No.
No. What is BCD? 10 BCD. What is the value of 10 BCD?
We need the 8.
Yes, you need 8 means 0, 0, 0, 1 and 0, 0, 0, 0. So you need 8 digits. But you are representing only 4. That's why after that you will use don't. Clear? How many K map? 4 came up and then draw the circle. Clear or not? This is the circuit. That means this circuit in input side ABCD you will place here. You can input as a BCD code and the result you will get as a X. Means you will give here 0, 0, 0, 0. The result will be 0, 0, 1. Right. Got it? This is the circuit. Now the next. Here, design a 7-segment decoder. Have you seen before anywhere this type of structure?
Yes.
Where? Watches, alarm, microwave, traffic signal. Where you want to represent the digit, even for token system, for everywhere you are using. This 7-segment display. Means you are going to design this, how it works. Look, if you want to represent in traffic signal 0011, you know it's 3. The normal person can understand? No. That's why you need this 7 segment. 7 segment will represent the decimal numbers 3, 2. So anyone can read this number. That's why. But now the question is, how can I convert? Using the combinational circuit. We will design it. Okay. So how we can design? We want to represent BCD number in 7 segments. You know the BCD number? How many inputs? 4 inputs, 0 to 15. You will write. After that, you want to represent 0. So if you want to represent 0, then what will you do? If you want to represent 0 means you are using A. These are 7 LEDs. Okay. Here, can you see A, B, C, D, E, F, G? These are 7 LEDs. So which LED you want to glow? Give 1. Which LED you don't want to glow? Give 0. So I want to represent 0. So for making the 0, how many LEDs I am using? I will use A, C, D, E, F. I will use 6 LEDs and G will be 0. Okay, so I will design like this. Can you see now? First, I am writing W, X, Y, Z, 0 to 15. I have 7 outputs. So if I want to represent 0, what I am going to do? All are 1 except G. Clear? I want to represent 1. So how can we represent 1, girls? B and C. So B and C will be 1. Others will be 0. Look. B and C are 1 and the others will be 0. Clear? I want to represent 2. So for 2, what should I do? A, B, G, E, D. Which one is 0? F and C. Clear or not? F and C. So how many came up? 7 came up. I will not give this question, of course, because it's too lengthy, but I added here just to clear your doubt, to clear, that means this portion should be clear to you that this course is related to your daily life. Means whatever the things you are using, you can design in this way. It's designed already in this. So you know, you should know the importance of this course. That's why I add this example so you can understand it is very useful. So you can design here now. If you can see in traffic signal 60 is written. So you want how many 7 segment then? 60. 2 7 segment, because 1 7 segment will represent the digit from 0 to 9 only. BCD. If you want 2 digits, 2 7 segment. If you want 3 digit, 3 7 segments. So you have to use these 7 segments, and 7 segments are also available in the lab. So you can also check if you want to check the result. If you want to check how it works, whenever you will give BCD 0 0, 0 will be there. If you give 0 0 0 1, 1 will be there. So you can check in the lab also. We have this kit. So this is called 7 segment display. Which question? Yes, of course, 4 came up here. Because 4 output, 4 came up. And in the next one, I told you 7 outputs. So 7 came up. Okay. And then you will design the circuit. Here it's mentioned 1, but you have to design for all. A, B, C, D, E, F, G. All K maps you will draw. Got it?
For the B, C, D. Until 9, right?
Yes. Then don't care.
But when we do it in the K map, doesn't it affect it?
No, you have to use don't K map with don't care.
I know, but sometimes we have one square. Doesn't affect that.
No. Whatever the rule I told you for the K map with don't care, you have to follow the same rule. Means if don't care, you already combine all ones and don't care left, no need to make the pair for me. Yeah, you can see even in the before example, it's there. Look, there are 4 K maps. Can you see? Look, some of the don't care is here. Look, no need to make the pair for these 3. Leave it. Whatever the rules I told you for the K map with don't care, you will use it. Okay. What? Yes. That's why I'm not explaining. We did before K map. I am telling you always that without K map, you cannot design the circuit. So your concept of K map, whatever I taught you before, it should be clear to you and you should keep in mind, then you will solve. Got it? It's the same K map, which we did it before. Now, design a 1-bit magnitude comparator. So 1-bit magnitude comparator means you are going to design a comparator circuit. 1 bit means, so if you want to compare, how many things you need? At least minimum requirement. 2 things. So you want how many variables then? 2 variable. At least you should have 2 variable. Variable A and variable B. Clear? But I want to design 1 bit. Means A has 1 bit and B has 1 bit. So maybe 0, A has 0, B has 0. Clear? A has 0, B has 1. A has 1, B has 0, and both are 1, 1. So how can I compare these numbers? Tell me.
Equal or not?
Very good. Equal or another? Greater than or less than. Okay. So we have these output means greater than maybe, then less than, and then equal. We will have 3 things. Clear? Now 0, 0. So A and B are equal, greater than or less than? Equal. Means this will be 1, other will be. Now 0 and 1.
Plus less than A is
A less than. So 0, then
0.
that's it. How many came up? 3 came up. Then draw the circle. That's it. Clear? This is called 1-bit magnitude comparison. If I want 2-bit magnitude comparator, then
Okay, so what is
this is designing a circuit. You know, whatever the things you are using in your daily life, it's implement using this technique. Maybe you have some device which can compare 2 numbers. How can you design like this? Okay. So designing is the circuit which you are using in your daily life. You are implementing in this way. You are designing. Whatever the idea comes in your mind, you should think how many input, how many output, and then design. Clear? Yes, if ABC means you are comparing between 3 things. So then how will you compare? Tell me 3 things.
from left to right?
First AB, then you will compare BC, then CA, like this. And it should be equal, greater than, so there will be several outputs. Huh? But here we were doing 1 bit. Now if I want to do 2 bit, A has 2 bit, B has 2 bit, means A has 0, 0, B has 0, 0. How many combinations?
4.
4. So how many combinations then? 16 combinations. That means you will compare now 2 digit together. 2 bit. I'm talking about 2 bit. So you will compare 2 bits. Means 0, 0, 0, 1. So you will compare in between them A and B. Means you will compare what is 0 and 0. 2 together. Which one is greater than? Which one is less than? Like this. Huh? You have 16 combination, then 3K map, and then design. Clear? So in the exam, we can give you maximum 2-bit comparator circuit, because 2-bit comparator circuit, you are using 4 variable K map. I cannot give you 3-bit magnitude comparator circuit. I cannot give you 4-bit magnitude comparator circuit. In the slide which you have, there is a circuit which is 4-bit, I think, huh? Which you cannot solve using K map. Okay, so I just add here to show you that this will be the 4-bit circuit, but we cannot give you, because it is if for this implementation you cannot use 4 variable K. Clear?
But we can use ABC.
Yes, ABCD means 2-bit comparator. A has 2-bit, B has 2-bit, then you are comparing
2
of
at a time? Or
2 at time. Yeah, 2 at time.
A with B, then A with C.
C is not here, dear.
If we have ABC.
ABCD you cannot do. ABC means there will be then A, B, C, then 2 raised to power. If 2-bit or 1-bit you are saying?
1 bit.
1-bit, then 8 combinations will be there. Then you can compare. 1-bit, 3 variable, you can compare. But if you have 2 bits, there will be 6 variable K map. You cannot do that using K map, because I didn't teach you. I teach you only 2 variable, 3 variable, and 4 variable. Okay. Yeah, no. You can just switch. There is no problem. You can write first A greater than B or A equal B, doesn't matter. Okay. This is called 1-bit magnitude comparator circuit. Even girls, this question I added here several questions. Still, it's not finished because in the chapter 1 you did several conversions. So all the conversion you can design all the conversion circuit. Okay. So whatever you done in chapter 1, complementary circuit, 1's complement circuit, 2's complement circuit, you can design for 2 variable, you can design for 3 variable, you can design for 4 variable because you know 4 variable came out. So it's better to design whatever the question comes in your mind. Means you want to design a circuit for the odd numbers. Check how many numbers of zeros are odd, how many numbers of ones are odd. Means any circuit, whatever comes in your mind, think how many inputs, how many outputs, design, draw the truth table, K-map. So any circuit, any idea, what comes in your mind, you can design. Clear? Okay. Now, decoder. Decoder and encoder. But before decoder, I will explain you encoder. Okay, so let me explain what is encoder and decoder. Okay, girls, as you know, I am Indian, huh? So my language is Hindi. You are Saudi, your language is Arabic. Clear? But in which language we are communicating? In English. So what I am doing from my end, from my side, I am transmitter, huh? I want to transmit some information to you. I want to communicate with you something. So what I am doing, I am converting Hindi to English. So English as a code, huh? So I am doing from my side encoding. What I am doing? Encoding. I encode my information into English. Then what are you doing from your side? Decoding. Means you extract the original information after decoding. You convert from English to Arabic to understand. So this is called decoding. So this process is called encoding and decoding, and the devices which we use, encoder and decoder. Okay. So decoder is to extract the original information, means at the receiver side, and encoder means the transmitter side, where you have to put the information into the code. Means you have to create the code to send your information. Clear? This is called encoding and decoder. Okay, and we will learn now encoder and decoder. So this is the encoder. Encoder is 4-to-2 encoder. How will you make the truth table for this? So we have A0, A1, A2, A3, A0, A1, A2, A3. I should write that. So you have A0, okay, A1, A2, A3. And then how many outputs? 2 output, B0 and B1. Clear? Now A0, that means this information you want to send. So what code you will decide for this information? Look. You will decide the code is 00 because it is at A0 position. Okay. This is the code. Now you want to send this information. Then which code you will decide? 0. Now, if this is the information you want to send, 1. And now this 1. Clear? Could you tell me what is the benefit of this? Why we are doing this? Hello. Why I am not sending as it is 1000? Why I am sending only 00? For protection. Yes, this is also a thing because we are coding in a different language. First thing. Another thing is money. We can save. How we can save money? If I want to send this 4-bit data, how many lines, transmission line I need? 4 bit. Okay, now how many I am using? First security, then the cost is less. Before I need to use, look, cost is just half. Okay, before I need to use 4 transmission lines. Now I'm using only 2 lines, 0, 0. Okay. And if I want to send all together, then there will be 4 and 4, 16 lines. Which will be, so one by one I am using, and I am using only 2. Okay, so it saves the money also.
Yes. We have bigger number than.
Yes, if we have 8 to 3, then if we have 8 inputs, then 3, 0, 0, 0. If we have 16, then 4. If we have 32, then 5. Like this. Just you will increase the number. Okay, A0 means 0 position, huh? Means this is the code 0, 1. If I am sending this information. So because it is at A0, so I will decide the code for this 0. Then A1, this is the message. But what is transmitting? This. So if someone is in the middle, can that person detect your information? No. Because we code in a different language. Clear? If someone doesn't know English, maybe you are, look, it's very easy example. You are talking in Arabic. Can I understand? I cannot. So your code is different. I cannot detect your code then. If I am talking in Hindi, then you will not understand. Same thing is here. So if you get this information, even you're not able to understand the original information because we encode. Clear? This is called. Understand? Yeah.
It's just the same for all and I think.
Yes, of course. This table is same. This is 4 to 2 table. Always. This is 4 to 2 table. Always. Huh? If you want 8 inputs, then there will be 3. If you want 16, then there will be 4. Yes, of course. Look, if you keep here 1, you will not write 0, 0 because it is A3. Whenever A0 is 1, then you will put 0. Okay. If A3 is here, definitely you will assign this code for. Clear? Otherwise, if we don't have any specific things, any person can do by their self. This is not the way. We should have some standards. Means if this is the code in this way and at A0 position, we have to write 0. If A1, 0. If A2, 1. Clear? Now, I made the box, but what is inside the box? How it is happening? How it will transmit this information into this decoder? But what is inside? Gates. Yes. Which gate? Check. Look. What is the value of A0? A0, how did you get A0? How did you get? Means I'm asking, what is the circuit inside? I just made a box, but in the box there should be some gates. Okay, so let's check. What will be the gate here? Can I delete now this? Okay, decoder and encoder pair. So now the image will be very much clear to you. So we did encoding at the transmitter side, and here we are doing the decoding. We will get the exact information what I am transmitting at the receiver side after decoder. Clear? But now I should know what is inside, which gate there should be. Okay. So how will you know? From the truth table. Here, this is 8 to 3. So 8 to 3 means 8 inputs and 3. So now I want to send this information. This is the information which I want. But I encode in I0. So I encode in 0. Clear? The information is I1. Means here should be 1. Means this is the simple code which the information which I want to send. But the code for this is 0, 0. Clear? Now I want to know what is inside the box. How can I know? So I should know how I will get y0. Tell me. Y0 I have, if means if I1 is 1 or y0, I3 is 1 and this and this. Means if this or this or this or this is 1, then y0 is 1. So I should use which gate? Or gate. Not and. And means if all are together. Here either this or this or this or this, then the result will be y0. Means y0 will be 1 if I1, I3, I5, I7 is. Anyone is 1, the result is 1. Anyone. What is the y1? I2, I3, I6, I7. And for y2, y2 is I4, I5, I6, I7. Means out of these value, if anyone is 1, the result is 1. Not all together, huh? That's why we don't have AND gate. If anyone, so we have OR gate. Clear? So now we can design the circuit. You can see. So we have OR gate, 3 output, means I am giving the 8 inputs and 3 output. And this is the box. So in the box, we have AND gate in this form. Inside the decoder box, encoder box. Clear? So I made a box encoder, but what is inside the box? Inside the box, we have in this shape, in this connected form. Or clear?
So the question will be drawing.
Question can come, yes, in the drawing, but we can, maybe I can show you this diagram and then we can ask what is it? To the power, yes, to the power of n, same thing. Look, here is 2 raised to power because there is 8 inputs, huh? So 8 to 3. Clear? 8 to 3. So 8 means 2 raised to power 3. So this 3 will be the output. You should know the output in terms of powers. Okay, means if I have 16 input, so how many output? 2 raised to power 4. So there will be 4 output. Okay. If we have 4, then 4 means 2 raised to power 2, so 2 output. So then 4 to 2 decoder. The powers of n will be the output. 2 raised to power 3. 3. So then 3 will be the output and 8 will be the input. Okay, 8 to 3 decoder means. No, I0 is always here. I0 you can represent, it's not connected to anyone, but it should, no need to delete because we have 8 inputs. So we should have from I0 to I7. Okay, we cannot delete it. We should have. Clear or not? Encoder. What are you saying?